The topic of our today's discussion is equations of equilibrium and 2 and 3/4 members. As such, our objective is to be able to learn and apply equations of equilibrium to solve for unknowns and also recognize 2/4 members. As such, there are certain activities, as we did with previous presentations, previous lectures. There's a reading quiz, applications, equations of equilibrium, 2/4 members. There's a concept quiz, group problem solving, and attention quiz to wrap the session up. So first, let's take a look at a reading quiz. The three scalar equations, summation of forces in the x direction equals to summation of forces in the y direction equals to summation of moments about point O equal to 0, are blank equations of equilibrium in two dimensions. Answer A, incorrect. Answer B, the only correct. Answer C, the most commonly used. And answer D, not sufficient. The correct answer is C. As you read your textbook, you would see that there are also two other forms of equations of equilibrium that are used, but they're not as common. So it's the most commonly used is the correct answer. Then for the second reading quiz, a rigid body is subjected to forces as shown. The body can be considered as a blank member. And as you can see, there's a body is shown here. There are forces F1 and all the way up to F6. They're acting on this body at point A and B. And we would like to know what would be the blank. The body can be considered as a single force, 2/4, 3/4, and the 6/4. So the body could be considered as a 2/4 member because we can draw a straight line between point A and B, and the line of action of the, well, this is not that straight, but you can, there we go. This is much better. You can draw a straight line between the point. Assume that this is a straight line. I didn't do a good job, but that's a straight line here. And that will be a 2/4 member. And also for the reasons that we would visit shortly, you would know why this is correct. So some applications of a 2/4 member, as we have seen similar applications. This is a truck ramp. It has a weight of 400 pounds. The ramp is pinned at A and held in position by the cable. How can we determine the forces acting at pin A and force in the cable? This is one of the applications of a 2/4 member, and after applying it, you would see how it would simplify the problem. The other application is, you've probably seen this in auto repair shops. An 850-pound of engine is supported by 3 chains, which are attached to the spreader bar of a hoist, and we would like to check to see if we exceed the strength of any of the members or the chain in this case. And then the question here is, how can you determine the force acting in each of the chains? That's where we apply equations of equilibrium and also 2 and 3/4 member concepts. Okay, so let me go over this rigid body as shown here. As you can see, this body is subject to a system of forces, P1, P2, A sub x, A sub y, B sub y, and so on, at different locations. When this body is in equilibrium, obviously the net forces and net moments acting on the body are 0. We discussed this earlier. And we also need to satisfy certain conditions. We're representing it by 3 scalar equations. Summation of forces in the x is 0, summation of forces in the y direction is 0, and summation of moment about any point O is set to 0. Again, O is any arbitrary point that we can pick. So these equations, and they are most commonly used, as I mentioned, and there are also other forms of equilibrium equations, and you can read the rest in your textbook. So if we could be able to if we would be able to identify two force members as we would discuss here, it would have been much easier to do some of our calculations, and it would really simplify if we can recognize the two force members in advance. Again, the two force members are subject to forces at only 2 points. In this case, point A and B is shown. As you can see, the line of action would go through a line, for example, AB here, F sub A and F sub B, we can connect these two points. For this one also, we can connect these 2 points, but because of the direction of these forces, there will be moment applied to the body itself. As we are trying to apply these forces, and you would see twists at AB and so on. But if you look at the first, actually the last one, this one that I am encircling in red, you should be able to see that for this particular member, there would be no moment induced by application of F sub A and F sub B, as long as they're in the same, they go through the same line of action as I just drew. So some of the examples are shown here. These are some of the cases. Look at AB here, although the member is a little bit curved, but it would still satisfy our criteria because it's already being connected at the third point. This one, A and B, again, it's a two force member. Forces are only applied at 2 points, A and B, and the line of action of the forces would actually go through this. Although the angle may not seem as obvious, but I can replace those forces by actually two forces here. I can do the same thing here and replace that by that, and I can put the other force here. Although there's a connection here in between, but it seems that because the line of action of these forces, they go through the same line, then that would satisfy the criteria of a two-force member. Again, it's going to simplify our calculations substantially, as you would shortly see. So how can we solve for 2D equilibrium problems? First, we need to establish an XY coordinate system. If that is not given, then we need to draw the good old free body diagram of the object under analysis. Then you would apply the three equations of equilibrium, E of E, or equation of equilibrium, to solve the unknowns. Also realize that in order for us to solve an equilibrium problem, we have some unknowns and we have some equations available to us. If the number of equations that are available are more than the available unknowns, then it will be an indeterminate situation, and we need extra equations to bring in either from symmetry or other types of conditions that we can solve the problem. And in many cases, we need to be familiar with some of the advanced structure analysis technique in order to solve for all the unknowns. But if there are more unknown than the number of independent equations, then we have a statically indeterminate situation. And again, the order in which we apply the equations may affect the solution. So we need to be smart about that and pretty much look at the problem first before we can just try to solve it, before we attempt to solve it. So it's very important to look at the problem and see what's the simplest and quickest way to solve the problem. Also, if the answer for an unknown turns out to be a negative number after we do all the calculations, then the direction of the unknown force is opposite to the assumed direction when we started the problem. So and that's how we can actually distinguish some of the tension and compression forces. So let's do an example. Given the 4 kilonewton load at B of the beam is supported by pins at A and B. So we have the situation as such. The beam is supported by pins at A and D, actually A, D, and C. We would like to find a reaction at A and C. We need to develop some kind of a strategy to solve such a problem. So let's take a look at that for a minute. Try to see what's the best way to do this. As you can see, the 4 kilonewton is applied at the end of beam B's. That would first we need to determine if what would be the reactions here at the support. So the first thing we do is we would determine that, and then we would draw a free body diagram, a complete free body diagram of the boom, and then we apply equilibrium, the equations of equilibrium to solve for the unknowns. Let's see how we can do that. So let's identify all the reactions. There are 2 of them here. This is actually not a roller. This is actually a pin support, as was given in the problem. We also have another similar type of situation down here at D. That's the same kind of a support that we have down here. But we're not really concerned. Well, we are concerned with that, but we're mostly concerned with the free body diagram. And so there'd be a force here as a result of the 4 kilonewton, and would be forces developed at member DC. And as you can see, we put all the unknowns there in order for us to, because we were actually looking for the support reaction at A and C, we are really not concerned with the D part of the equation, although we may use it to solve the problem. Let's see how we do this. So we would recognize first that if there are any 2 force members, we realize right away that CD is a 2 force member, as you can see, and as such, the number of unknowns at C are reduced from 2 to 1, and that will be only the reaction of the support at C. Then if we use the equations of equilibrium, we would get the summation of moment about point A. And how many unknowns we have? We have actually 1 unknown, and right away we would actually solve for F sub C to be 11.3 kilonewton. Okay. So right away we know what the reaction would be at C by actually picking a smart point to take the moment about. Okay, so we just take the point E, because if I wanted to take the moment about other points, any other points, well, I could have taken the moment about point C, and then from there I would actually calculate A sub Y, knowing that there's a 4 kilonewton at the end, and I would come back later and calculate the C. So both methods would be possible, summation of forces in the X. And this, so first we did the F sub C, then in order to calculate A sub X, again we take the summation of forces in the X, A sub X plus 11.31 cosine of 45 degrees would be 0, and that is actually the X component of this force. Remember, F sub C is going to have 2 components. One is horizontal, one is vertical. Since this angle is 45 degrees, then the F sub C sub X, which is the horizontal component of F sub C, would be 11.31 cosine 45 degrees. We set that to 0. We solve for A sub X as minus 800 in kilonewton. Then we do kind of like using the similar equation, but of course now we're dealing with summation of forces in the y direction. We set that to 0. In the y direction, we have A sub y. We also have the y component of F sub C, which is 11.31 sine of 45 degrees. And remember that there is a minus kilonewton force acting in the y direction, and the answer would turn out to be a sub y minus 4. Now we have two negative answers. Remember, originally we assume this is upward and this is to the left. It actually turns out that this should be downward and this is to the left. So the original assumption that we did with the direction of the forces turned out to be actually not correct. So again, the magnitudes are correct, but the direction of a sub x and a sub y would be different. But the direction of f sub c is correct because we assume actually kind of upward, right, to the right and up, more like in an angle, and that is also correct. So let's take a look at a concept quiz together to see so far what we've been doing. Remember, these concept quizzes, they are given so you can check what you've just learned. So for this beam, how many support reactions are there, and is the problem statically determined? Okay, so how many support reactions do we have here? Let's identify those first. This is a roller, so we're going to have one here. This is also a roller. We're going to have another one here. This is also a roller, so we're going to have three reactions here. There are three reactions. There is a force F. Again, depending on if the F is known or unknown, the answer is that we have actually three unknowns. Assume the F is known. Otherwise, if the F is unknown and all the reactions are unknown, what is it that we are trying to find here if everything is unknown? So the D here is 3, and no, it is not statically determined. Okay, we have 1, 2, 3 support reactions, and the F is also, if F is unknown, this is statically determined. If F is not unknown, then it's statically indeterminate. And actually, this is unstable condition because as we apply the load, the structure has a tendency to move to the left. So this is actually not determinate, and there are three support reactions that are associated with that. So 3 support reactions, but it is statically indeterminate. The beam AB is loaded and supported as shown. How many support reactions are there on the beam? And is this problem statically determinate? And C, is the structure actually stable? So let's identify the support reactions. They're both fixed. So the reactions at the support here, actually there would be a fixed support here, and for a fixed support there would be an XY component. There's also a moment. Let's assume the direction of it is in this direction. And first, how many support reactions are there on the beam? There's one here, and again we can pretty much look at those. There are 3 and 3, 6. However, there is no answer 6, and we are only looking for the reactions, not the moment. So we didn't include the moments here. So this is out and this is out. So there's only 4. So the answer is either A or B. Let's concentrate to see if the answer is which one is the correct answer. So it's either A or B. I'm going to put a little line on it. Then the second one, is this problem statically determinate, yes or no? Well, we have obviously more unknown than the available equation. So this is really statically indeterminate. So it is no is the correct answer. So that would leave us with really part B. And is the structure stable? Yes, it is stable because under the application of load, the supports are rigid, and there will be no um, um, instability caused in the structure. So the correct answer here is actually B. So let's solve a group problem, and we would actually wrap our session up. So there's a jib crane. It's given here. It's supported by a pin at C right here. This is the pin, and there's a rod AB that's also supported here. And the load has a mass of 2,000 kilogram with its center of mass located at G. We assume X, this distance, to be 5 meters. This is supposed to be 5. And I butchered it, of course. Okay. Then we would find the support reactions at B and C. So first, let's establish the XY axis. Then we would draw the complete free body diagram of the jib crane. And then we would apply the equations of equilibrium to solve for the unknowns. Let's get to that. So at C, there's C sub X and C sub Y. We assume an arbitrary direction, and we would change them if the answer turned out to be negative. And for AB, we are doing the same thing. There's a force developed at AB. Again, this is the entire free body diagram, complete free body diagram of the beam. The application of the load here also would help 2,000 times 9.81 to complete the free body diagram. Then we would first write a moment equation about point C, and that seems to be simpler. Right away, it would eliminate two of the unknowns, C sub X and C sub Y. So we would take the moment about the point C sub X first, okay? So as a result, as you can see, we are going to pretty much solve it for that. The 3/5 of F sub AB and the 4/5 of F sub AB. Those would provide us with F sub AB. If you take the summation of moment about C here, okay. And that would provide us with F sub B as 38.3 kilonewton. Then we would continue our calculations, and we would take the summation of forces in the X and in the Y direction. We set that to 0, and we can actually solve for C sub X and C sub Y as such. So the first one is the 4/5 of 38320. This is the F sub AB. Remember, this is going to have two components. One is in this direction, the other one is in this direction. Of course, got to be a straight line. Okay, this is the direction of the arrow. I usually show the arrows like that. Okay, so please keep that in mind, or I would actually show it, well, not like that, but the way I actually show them up here. Okay, so the X component and the Y component, the X component here and the Y component, and remember we need to include both of those when we are taking the summation of forces in the X and Y before we set it to 0. In the Y direction, we also have the 2,000 times 9.81 that should also be included in the equation. Okay, let's take a look at an attention quiz here. Which equation of equilibrium allows you to determine F sub B right away? In this case, the equations of equilibrium are given. Summation of forces into X is 0, Y is 0. Summation of moment about point A is 0. The first one, let's see which equation of equilibrium would allow us to determine F sub B right away. We've done two problems similar to this. A summation of moment about point A would actually eliminate the other unknowns except F sub B. So that would actually help with that. Okay, summation of moment about point A, and that's the correct answer. The second attention quiz before I wrap it up. A beam is supported by a pin joint and a roller. How many support reactions are there, and is the structure stable for all types of loadings? And the four answers given: 3 and yes, 3 and no, 4 and yes, 4 and no. And you would try to find out what the answer would be. So we have one pin joint. There are two reactions there for the pin and a roller right away. And the answer is either A or B. And is the structure stable for all types of loading? That's a very good question. Is it stable for all types of loading? Well, for sometimes it is. For some types it is. For sometimes it is not. For example, you can see that it could be certain situations in which a moment could be applied and the structure becomes unstable and so on. So the answer is 3 and B, no. So that would be the answer here. That brings me to the end of today's lecture. If you have any questions, please feel free to contact me. Let learning continue. Thank you.